Hey, hi there. Welcome to the fourth session of hypothesis testing. Today we'll be covering another kind of hypothesis test, which is used extensively in the real world scenarios, and that is called as ANOVA. ANOVA is called as analysis of variance. Okay. To start off with, we'll only do one-way ANOVA as of now. When we apply ANOVA in the case studies which we are going to do after this video, they will be covering the two-way ANOVA as well. Okay. The underlying concepts are same. So the one-way analysis of variance is used to determine whether there are any statistical significant differences between the means of two or more independent groups. For one-way ANOVA, the ratio of the between group variability to the within group variability is found out. So basically what they're trying to say here that ANOVA can be used to find out differences between means of multiple samples. In Z-test and T-tests, and in fact chi-square tests, whatever we are doing so far, we are comparing, either we are dealing with one sample or we are comparing with two samples, right? But an ANOVA will allow you to compare means between multiple samples, more than two samples as well. Okay. And the value which we find out in ANOVA, just like we had the Z statistic, the T statistic, the chi-square statistics, here it is called as the F statistic. Okay, it's called, the ratio is called the F value, or sometimes it is called as the F statistic when the null hypothesis is true. So basically the data is again assumed to follow a F distribution when the null hypothesis is true, just like we had for chi-square, we had for T-test as well. Okay. So this ratio is nothing but the ratio of the between group variability to the within group variability. Now these 2 points, please remember, between group and within group. But what is within group variability and what is within group variability? Let's have a look. So let's say we want to compare 3 sample means to check if a difference exists between them. Okay, 3 samples. So let's say my 3 samples are X1, X2, and X3. I'm noticing I'm giving bar here. I'm considering them to be symmetrical. So in a middle point, we typically have X1 bar. That's why I'm putting it like that. But typically it's X1, X2, and X3. The means basically, right? Okay, 3 different samples. Now, some of the questions which I may ask is, do all these 3 means come from the same population? Right? This is one question which we have to think about. Second is, or maybe that is one mean so far away from the other 2 that it may not be from the same population like the other 2. Or it can be also that all the 3 means come from their 3 different respective populations. Right? So basically, when you talk about hypothesis testing in ANOVA, by using ANOVA, the null hypothesis says all population means are equal. That is a predefined null hypothesis. All population means have to be equal. So basically what they're trying to see, all the samples come from the same population. Alternate hypothesis will say not all of the population means are equal, but or at least one of the pair do not come, or at least one of the pair are unequal, and that's why they do not come from the same population. Right? So if I may explain a little bit further. So here, all populations means are equal means what? That all of them come from the same population. All samples come from the same population. This basically means that probably at least one of them, let's say rest everything is equal, but mu1 is not equal to mu2. Rest everything is mu2, mu3, mu4 may be same. At least one pair. If I say at least one pair, it may be 2 pairs, 3 pairs, 4 pairs. Even if one of the pairs are unequal, my null hypothesis will be rejected. For null hypothesis to be true, all the population means have to be equal. They must come from the same population. That is what is assumed in null hypothesis of ANOVA. Okay. Now, if you remember the second slide, I talked about variability between and variability within. So let's look at what does variability between mean. Okay. So variability between means that among the 3 samples, how different are they from the overall population, right? Okay, how far is X2, X3, X1 from the main population? Okay, sample means are far away from the overall mean. That is what is meant by variability between, and that is where I will calculate the sum of squares between. Please remember this notation will be this parameter will be calculating this parameter in our calculation of F ratio. Okay. Now let's look at variability within. Now, if you look at variability within, so you can see here that the sample themselves may have a high variance in them. Means the standard deviation, the shape is pretty much flat, right? This is where we look at SS within or sum of squares within. So what am I trying to say? What I'm trying to say here is that the total sum of squares or total variance can be attributed to two reasons. One is the sum of squares between and the sum of squares within. And because of these two sum of squares or these two variants, my sample mean may not come from the same population, right? Okay, and that is where we'll go to the next step, where we try to calculate the F ratio using an example. So let's try to understand it directly using an example rather than going to the theory of calculating F ratio. Okay, let's say we have three groups of samples of factory emissions of different plants of the same company were collected. The score is computed based on the composition of the emissions. We want to find out if there is any inconsistency or difference across the three groups. So basically, we had three sample factory emissions of the same company. There are three factories here in different locations of the same company. There's a company called ABC where they have three different, say, or XYZ, whatever it is, three different plants in three different locations. And we are basically extracting or keeping a record of the emissions from all of these different samples or three plants. Let the plants name be A, B, and C. Okay, let's say we have these three emission values, three sets of, let's say we have these three different plant names, and these are my respective emission scores from each of these plants. Okay. Now, the question is asked is, we want to find out if there is any inconsistency or difference across the three groups. So what does the null hypothesis will say? The null hypothesis is very simple. It will always say mu A is equal to mu B equal to mu C, which means that the emissions from all these factories come from the same population. There is no much significant difference in the emissions of these plants. And that is how the company has to abide by this regulation. There are certain regulations in factory emissions, right? And they have to abide by those regulations. Correct? If one is giving, say, it is abiding by the rule, and the another plant is significantly higher emission, that will not work out. There is inconsistency in the emissions, which should not be the case. But my hypothesis will say this, and my alternate hypothesis will be not equal to not equal, or any one of them not equal, whatever it is. Similarly, ANOVA test is typically used in medical industry also, where you find out the parameters of a medicine, the effectiveness of a medicine on a drug, right? So it's very, very important. It's most highly extensively used hypothesis test in the real world. Now, so these are my hypothesis statements. Null hypothesis will say mu1 equal to mu2 equal to mu3, which means the factory emissions are same across all the plants, right? And alternate hypothesis will say there is inconsistency or difference across the three plants. The tougher situation always, so in ANOVA, we don't have to bother too much about the statements. Why? Because by default, null hypothesis will say mu1 is equal to mu2 is equal to mu3 is equal to whatever number of samples you have. Now let us have a look at the solution. How do we calculate the F ratio? So first thing which you have to note down is that the number of samples. The number of samples is K and the number of data points is N. So here my number of samples is basically 3. Number of data points means data points from all the 3 samples, total N. Okay, that is what N, capital N means. Step 1, what do we do? Here we calculate 3 things. Alpha is already assumed, right? So if you look at this, alpha is already assumed. We calculate 3 things. Degree of freedom between, degree of freedom within. I told you in the first slide itself, right? F is nothing but between to within variability ratio, right? So we have to calculate 2 degree of freedoms here, degree of freedom between and degree of freedom within. Degree of freedom between is K minus 1, number of samples minus 1, 3 minus 1 is 2. Degree of freedom within will be total number of data points minus the number of samples, which is 59 minus 3, which is 6. 59 is the N value here. So this is called as between, this is called as within degree of freedom. I'll also calculate the degree of freedom total, which is n minus 1, 59 minus 1, which is 58 total. Okay. So once we have this and we have the alpha parameter, so all these information, all the 2 degree of freedoms, 3 degree of freedoms, and my alpha value will help me in calculating the F critical from F table. Very simple. And that will be 3.161. Okay. For this particular data set. In step 2, I'll be calculating the sample means and the overall mean as well. So this which you see here, M is nothing but the mean of sample A. This is the mean of sample B and the mean of data points in sample C. And this is the mean of all these 59 values which we have in our overall data set. Right. Now, what do I calculate from here? From here, I'll calculate something which is called as sum of squares. So SS means sum of squares. Remember, I mentioned this in one of the few slides where I was talking about sum of squares within and sum of squares between. Okay, so sum of squares total, I'll first calculate, and that is my XI, all the individual data points, 59 individual data points minus the overall mean whole square. Right, correct? And that value is 8548, which you'll be able to easily calculate. Sum of squares within will be, it's a within sum of squares. So we calculate the sum of squares between each sample individually, and then you'll add it up. So there will be 3 summations. Why? Because for sample A, it will have its own sum of squares. Right? So that's why you'll be subtracting the mean of sample A from the data points which are in sample A only. And similarly goes for B and C. And that summation total will give me 7096 in this case. Sum of squares between also we can calculate is no formula, but here it is easier to calculate. Why? Because we already have calculated the sum of square total. That's why you can simply subtract the sum of squares within from the sum of squares total. Remember, I told you the total sum of squares can be attributed to 2 things. One is within sum of squares, and one is between variance, between sum of squares. In fact, in one of the slides I mentioned the total sum of squares is equal to SSB plus SSW. Now this is step 2. So step 1 focuses on calculating the F critical, just like we did for other hypothesis test. Step 2, we have to first calculate these sum of squares values. It's a bit lengthy process than the other hypothesis test, because in other cases we directly calculated the statistical value in step 2. But here we'll first calculate the sum of squares, and then in step 3, I'll be calculating the mean sum of squares, the average sum of squares. Now, mean sum of squares, while calculating, very careful. You simply cannot divide it by n. So for sum of squares between, I have to divide it by the degree of freedom between. For sum of squares within, I have to divide it by the degree of freedom within to get the mean sum of squares for within. Since I have the mean sum of squares between and within, this is nothing but my variance, my variability. Because variability is always the average of the sum of squares, right? Correct? So degree of freedom is nothing but the component which will help us to create the mean sum of squares for between and within here. Once we have done this, next what we do is we calculate the F statistic, which is the ratio of the mean sum of squares of between to the mean sum of squares of within. You can call this as variability between divided by variability within as well. So once we have calculated the F statistics value, which is 5.73, now I can compare with the F critical value, which was 3.161, right? So now my F statistic is greater than my F critical value, and any statistic which is greater than the critical value, my null hypothesis will always be rejected, which means that there is a significant difference across the 3 groups of plant emissions. The process is same. It's just that the calculation of these statistics varies from test to test. For t-test, the formula is different. For z-test, the formula is different. Chi-square, different formula for both test of variance and test of dependence. Now, in here also, one way ANOVA also, we have a different calculation of the statistic value. Similarly, we have Similarly, we have ANOVA 2-way with replication, without replication. Process is same, just that the formula changes. But we apply we'll apply ANOVA two-way directly in our Python notebook. That is where I help you explain the concept as well. No problem. Okay. So guys, you can see how easy it is to apply. Now let us try to see how we calculate P and F statistic in Python. Okay. So it takes one single line of code again to calculate P value and F statistic in Python. We can then compare the P value with the alpha. Once I calculate the P value. Now, how do I calculate? We use something which is called as stats.f underscore one way. So one thing, guys, which you have noticed so far is that the library which we were using to, or the model which we're using to calculate all these, perform all these hypothesis tests is same. And this stats model actually comes from scipy.stats. Okay, the scipy module. And this is .f underscore one way, right? This is the function. For two-way with and without replication, also we have respective functions. And it is very easy to use ANOVA one way in Python because all that it requires are a three group of data points, three sample data points separately in arrays within the function. Okay, so suppose the same way we have the data points, right? A, B, C. All I have to do is put the entire array of the data points in each of these arguments. And what does it calculate? It helps me calculate the F statistic and the P value for a two-tailed test. So for one-tailed test, we have to compare P by 2 with the alpha. So by default, this function gives me the P value for a two-tailed test. So if you have a one-tailed test, then to compare P by 2 with the alpha value. Okay. Similarly, we can we can calculate the F critical also with a single line of code. And then we can compare the F critical with the F statistics either way. So now if we can look at the formula, the function which we use is stats.f.ppf of 1 minus alpha comma degree of freedom between and degree of freedom within, because it is a ratio of between by within, right? Correct? That is how it is. Sometimes it will be written as degree of freedom numerator divided by degree of freedom denominator also. So in a numerator, we have the between variability and a within variability is on the denominator. So this is for a one-tailed test and this is for a two-tailed test. You have to do 1 minus alpha by 2 to calculate the F critical value. So so there is not much difference in the syntaxes. It's just that some of the arguments will keep on changing off with respect to the different hypothesis tests which we do, right? But the model is exactly the same. The function, the ultimate function is ultimate PPF only, right? And we have an F module which will have all these sub functions for calculating F critical. Okay, so guys, what did we learn today? We discussed about ANOVA test. In ANOVA, the null hypothesis and the alternate hypothesis almost predefined, because null hypothesis will say all the population means are same. The alternate hypothesis way all population means are different, which means the samples are from different populations, right? Secondly, it allows us to compare more than 2 samples. Thirdly, although we are commenting on the mean, ultimately I'm using sum of squares of variability to calculate the F ratio, right? And the F ratio is nothing but the ratio of the between variability by the within variability. So after calculating the sum of squares between and sum of square within, I have to calculate the mean sum of squares between and mean sum of squares within. Correct? And to divide it by the degree of freedom between within. Critical value is dependent on 3-4 factors: alpha, degree of freedom within, degree of freedom between. We also have a degree of freedom total, which is nothing but equal to n-1, total n-1. Right? We also got to know how to calculate the F critical value from the F table. I'm not showing you the F table, guys. It's as simple as what we had done before, right? Just like we did in, for the other tests as well. So I hope you're learning, guys, and I hope you're finding it interesting. Please check out the application video as well. We'll be doing ANOVA in Python from scratch on real world data sets and how are things done in the real world. We'll also do ANOVA two-way. Okay. All right, guys. Wish you happy learning and see you in the next video.